Hi. So in this video, we're going to talk about linear dependence and linear independence and kind of go from there. So last time we talked about vector spaces and stuff like this. And so what one might ask is, well, how do we kind of what's a good starting point for, how are the vectors related to one another? And a lot of times we're going to do this through something called linear combinations of vectors. So linear combination of vectors, if you haven't seen this before, it's just we take a bunch of vectors, we take some scalar multiples of each one, and we add them all together. So in essence, we have exactly that. So we have, this is how we'll denote it. So here you'll kind of notice that we have some scalar multiple of some vectors. And we just sum them up. So here we have m of them. So I is equal to 1. So here's the first term, all the way up to the last term, m. And that's it. So here we'll denote, as we kind of have, lambda I is scalars. So here, real numbers. But remember, it doesn't have to be real numbers. We could have taken rational numbers, complex numbers, finite fields, etc. And then vectors coming from the vector space. And then what we're going to define, the first thing we're going to define is linear dependence. So basically the idea here is when is one set of vectors, or when is a vector dependent on other vectors? In other words, it's a linear combination of some other vectors. Well, when is this the case? So we have linear dependence. This is basically if there's exists some lambda 1 up to lambda m of these vectors x1 to xm. So we start off with some x1 to xm vectors. They're going to be linearly dependent on one another if there's scalars such that the following holds. Lambda 1, x1, lambda 2, x2, all the way up to lambda xm, if this is equal to 0. Vector. These are vectors. And why are we call them linearly dependent? That's because if you look at this equation, I can take any one of these components and I can move it to the other side, right? And you can see then that that one vector is dependent on the other ones. So we can kind of see this, right? So if I take an xi, so if I move xi to this side, minus lambda, minus lambda I xi. So on the left-hand side, we'll have lambda 1, x1, all the way up to lambda I minus 1, xi minus 1. These are vectors. Plus lambda I plus 1, xi plus 1, all the way up to lambda m, x, m. So in other words, xi is some sort of combination of the other one. So it's dependent on it. So now if this is not the case, if I have a set of vectors where I cannot make them equal to 0, where all of the scalars are... So one thing to notice here is I'm specifically specifying that they're not all equal to 0. Because obviously if I make them all equal to 0, this is trivially true. We're not really getting any information. So if this is not possible, then we call them linearly independent. In other words, one vector is not dependent on any of the other ones. And so like that little note I said is already here. So I've already mentioned this. So a little note that we can't have them all be equal to 0. And so, okay, so we have the set of vectors. And it might be a little difficult sometimes to show that. So if we're trying to ask, okay, well, how do we know if something is linearly independent, right? It's a little complicated to kind of show that if I have lambda 1, that it's impossible to have lambda 1 x1 plus all the way up to lambda m xm is not equal to 0 for any choice of lambda, right? Like it's a fairly difficult thing. Luckily for us, there's actually an equivalent definition. So an equivalent definition of linear independence turns out that we can actually just do the following. We just take our vector. So we set everything equal to 0. So we set mu1. I guess here we'll do lambda 1 to keep things with the notation. Lambda 1 x1 all the way up to lambda m xm. So we set this equal to 0. Now we know this is true if and only if, so this is the new thing. This is true if and only if lambda 1 is equal to lambda 2 is equal to lambda m equal to 0. In other words, one thing we can do is we can just set everything equal to 0, and if we can prove that all of the lambda have to be 0, then we know there it's independent. Like if this whole property is true. So in other words, the way to kind of see this as a proposition, like to put these together, is the vectors are linearly dependent if and only if at least one of the vectors can be expressed as a linear combination of the other vectors. So this is the thing that I was just talking about previously. So this here, there we go. This here was precisely this operation here that I was doing, right? So in 1.3. The 1.3. Cool. So what we're going to do is we'll stop here. I'd rather have shorter videos, if you haven't noticed. So we'll stop here and we'll talk about basis and dimension in the following video. So I will see you then. Peace.